here. So with this first problem, it's a three-part problem. The first part says sketch the graph of y equal to g of absolute value of x. The second part says sketch the graph of y equal to the absolute value of g of x minus 1. And the third part says find the domain of the function y equal to 1 over f composed with g of x minus 1. So with this first problem, with these first two problems actually, I really want you to notice where the absolute value is occurring. On the first problem, it's inside the parentheses of the function. The absolute value is appearing on the domain variable. In the second problem, the absolute value is outside of the function. And here we're taking an absolute value of the range. Okay, so in both cases, where the absolute value is will affect the graph. So one reason I did this problem is because, you know, I'm obsessed with the absolute value. So absolute value will show up on the test, and you have to be able to like write down the definition. For example, what's the definition of absolute value of x minus 1? So here, I want to decode this. Remember, the absolute value function is a piecewise defined function. So this entire expression is actually a piecewise defined function. So I first define the absolute value of x minus 1. So you remember the definition. The definition says the absolute value of blah, so here blah is x minus 1, will equal blah if that blah is positive. And the absolute value of blah will be negative blah with the minus sign if blah is negative. So here blah just happens to be x minus 1. Okay, so here's what g composed with absolute value of x minus 1 looks like. It's the same definition, except now I've applied g on the outside to the function because it's g of the absolute value. So here I've done g of the absolute value here. Here also I distributed the minus sign and wrote it as 1 minus x. Finally, now if you plug it into the function, so g is the positive square root of x. If you plug it into the function, g of x minus 1 looks like positive square root of x minus 1 if x is greater than or equal to 1, and positive square root of 1 minus x if x is less than 1. And so now, you know, we would graph each piece. So basically, I would use our translations and transformations and stuff. So for this first function here, positive root x minus 1, we start with the function, start with square root of x, and then shift it 1 unit. And so that part should look like something like this. For the other piece, for this piece, I like to be a little bit careful here. Sorry, let me do. I like to be a little bit careful here with the minus sign. It helps to think about what the domain is. I like to think of this as put the minus out and do x minus 1. And I like to do the reflection first. So this minus sign right here, so starting with square root of x, that minus sign causes a reflection. So it flips. And then this minus 1 here, that's a shift to the right 1 unit. So if we put the two pieces together, this is what we get. This is the root x shifted 1 to the right, and then root of 1 minus x. So that's, we took root x, we reflected it about the y-axis and shifted it right 1 unit. And so that's what the graph looks like. And for me personally, you know, the key to being able to do this problem is I have to be able to rewrite this expression in this form. Being able to decode the notation and unwrap the notation and get down to a piecewise defined function where I can clearly see, aha, if x is bigger than or equal to 1, this is what the function looks like. If x is less than 1, this is what the function looks like. At that point, it's very explicit. I can just, once I have it in this explicit form, you can just graph each piece. So to me, getting to the piecewise defined definition here is really important because the brain doesn't really understand an expression like this is not really meaningful. This makes a little more sense. This we can connect up to this picture a little better. So with the other problem, the absolute value of g of x minus 1, you should think about where the absolute value is. Here, we're taking the absolute value of the entire output. So typically the way we think about doing this problem is first graph the function in between the absolute value bars. So first I graph root of x minus 1. And so, root of x is like this. Root of x minus 1 shifts it down 1 unit. And now, when we take the absolute value here on the outside, anything that was originally negative has to now be flipped because absolute value is always positive. So this portion here that was below the x-axis, when we take the absolute value, has to be flipped up. And so that portion will end up coming up here like this. So here's the graph. You can see this section is just root x minus 1 right here. Then the portion that's below the x-axis, that has to get flipped up, and that's right here. So at the end of the day, we see here's the graph, this thing here. The negative part flipped up so it's not negative anymore, and then the rest of the function. So in both cases, the absolute value occurs in a different place with a different result. So you should take a look at where the absolute value is occurring and compare and contrast the two. So for part C, it's a composition problem. And I want you, with composition problems, finding the domain can sometimes be tricky. And with a composition problem, you should remember it's like taking a connecting flight. If I don't have the ticket to make my connection, then I can't get on that flight. I can't make the next flight. So it's the same thing here. Here we have 1 over f composed with g composed of x minus 1. So first thing that's really important is that this definition, this notation. That f composed with g, x minus 1 means this. It's f of g of x minus 1. And here, this g function, this is the first connecting flight that we have to be able to make. Now, g of x minus 1 is the positive square root of x minus 1. And for even root, square root, 4th root, 6th root, we can only take the even root of a non-negative number. So here I need x minus 1 to be greater than or equal to 0. If you move the 1 over, we have domain restriction for g of x minus 1 is that x has to be greater than or equal to 1. So moving forward, no matter what happens, this domain restriction has to be one of the domain conditions that we take into consideration. So x greater than or equal to 1 will factor in later. So now let's actually calculate g of x minus 1. I replaced with this root x minus 1 right here. And now let me do f of root x minus 1. Remember, f is the squaring function. So I'm going to take root x minus 1 and square it. So this is x minus 1 to the 1/2 squared just gives me x minus 1 in the denominator. Now, here's where I have to think about the domain restrictions. So for this denominator, usually the domain restriction is x cannot equal 1. But in this case, we also have to take into account this domain restriction, that x has to be greater than 1. So now I'm intersecting, I'm combining the two. So if we take x greater than 1, combined, so x greater than 1, combined with x greater than or equal to 1, combined with x has to be greater than 1, gives us this has to be the domain. So we combined x greater than or equal to 1 with x not equal to 1. That gave us x strictly greater than 1. You know, and think about the connecting flight idea. If x is not greater than 1, root x minus 1 doesn't make sense. And so we wouldn't be able to make this connecting flight. Even though the final answer looks like it's fine, it's not really about the final answer. It's about the journey that the x variable is going through. And that involves, you know, you get x minus 1 and then it's under a root. So that gives us this domain restriction. So yeah, I think domains are really important, and just being able to, in general, understand what's going on with the composition, and that the function has to make sense at every stage. And so the domain is chosen that way.
So I have a question.
Yes, please.
Yes, me too.
For C, why is the domain x is greater or equals to 1?
It's not. The domain is x greater than 1.
Yeah, but what does it say that?
Here,
yeah.
For here, it's okay to take the square root of 0. This function is defined for greater than or equal to 1. Just the g of x minus 1 part.
Yeah, I get that. Yeah, okay.
Because it's okay to take, you know, square root of 0 is 0. Sal, did you have a question?
Yeah, actually, if you don't remember the shape of the curve, can we take 4 or 5 points?
Yeah.
Got it.
Yeah. But of course, the basic curve shapes, you know, I would strongly recommend that we commit to memory. But yeah, you should be able to plot a few points and get the general shape typically. It sometimes can be a little more time consuming, right? So I would recommend knowing the shapes, but you can also plot some points. Let me check here. So there's a question over the chat saying, are the spring 2018 and spring 2019 tests good indicators? Those are good indicators, specifically the spring 2019. So be careful. I think the spring 2018 has a derivative problem, but that's because in 2018, our calendar was slightly different. Definitely the spring 2018, spring 2019 are good representations of what you'll see a little bit later. So that was, yes, go ahead.
I have a question. Okay, so are we gonna go over like an A, B, and C piecewise like problem?
Yeah, like for the continuity.
It's just like solve for A and B, or like solve.
Yeah, that's like a continuity problem. Yeah, I hope I can get to it. It's on slide 7.
Okay.
Yeah. So I'm gonna try. Okay, so the next problem says classify the discontinuities of this given function. We won't worry about the function right now. And then they say, does the function have any vertical asymptotes? And to answer the question with limits. So for both classifying the discontinuity and finding the vertical asymptote, for me, the approach is the same. Think about the domain. For a function to be continuous at a point, that point has to be in the domain. So if a function is not going to be continuous, there's a good chance it'll be at a point where that's not in the domain. You know, another place where it could be where the limit from the left and the right don't agree, you know. So with the vertical asymptotes, again, typically vertical asymptotes occur at the roots of the denominator. You know, and again, that is a domain issue. So for me, I ask myself, what's the domain of this function? I start by thinking about what's the domain of this function. And now the way we answer the domain question is restrictions. We think about the restrictions. We are never allowed to divide by 0. So here I have something in the denominator. I need to check when is this thing in the denominator equal to 0. For those values where the denominator is equal to 0, I have to take those out of the domain. And the other restriction that we're typically trying to be mindful of is we never take the even root of a negative number. Here there are no even roots, so I'm not worried. So here if I factor the denominator, we get x plus 1 times x minus 3 using reverse FOIL. And so this function will be 0 when x is equal to -1 and or when x is equal to 3. So these are the roots of the denominator. This is potentially where the function is going to have a vertical asymptote or an infinite discontinuity, or maybe even a removable discontinuity. It's possible that it'll cancel with something in the numerator. Actually, it will, right? This x minus 1 is going to cancel with this this x plus 1 will cancel with the x plus 1 in the numerator. So these are roots of the denominator, but we need to check with a limit. What exactly is happening? Is it an infinite discontinuity? Is it a removable discontinuity? What's going on? So for -1, I take a limit. I'm checking the limit as x goes to -1. If this equals f of -1, then the function's continuous. You know, that's why I'm checking a limit. Continuity is a limit definition. So I replace the function, you know, with its definition, and if you try to plug in, we get 0 over 0. If you try to plug in a -1. So 0 over 0 is an indeterminate form. That means we need to do something, you know, some further math. Typically, our options are to multiply by the conjugate or factor and simplify, squeeze theorem. Here, because of the form, because I see there's something in the denominator that can be factored, and because once we factor it, it'll cancel, that's what we need to do here. Simplify this thing and try the limit again. So when I cancel the x plus 1s in the denominator and plug in a -1 for the x, we can calculate the limit is -3/4. So here, the limit exists, but the function's not defined at the point. If I try to calculate f of -1, if you plug in a -1 into the function, not the limit, into this function up here, in the numerator, I get 0. In the denominator, I get 0. So the actual function is undefined, but the limit of the function is defined. So here what that means is whatever the graph looks like, at x equal to -1, we have some type of hole, because the limit from the left and the right exist, but the actual function at the point is undefined. So yeah, when the two-sided limit exists, but the function's not defined, that's when we have a removable discontinuity. I do want to make one comment here. When I was taking the limit, I did not do anything about the absolute value function. I just left this as an absolute value. Why? Because for this absolute value of x plus 4, it will change its definition around the number -4. So here, so you can think if like you plug in x equal to -5, plug in a -5 there, that'll be a negative number. But if you plug in x equal to -3, that'll be a positive number. So the absolute value changes. Oh no, I didn't do that. The absolute value changes its definition around -4, excuse me. So here we're taking the limit as x approaches -1, and we're very close to -1. So in this case, I can just treat the absolute value like a regular function. I don't need to necessarily look at its piecewise definition. I can treat it like a regular function in the sense that I can just plug in the number into the function when I'm trying to find the limit. Because to the left of -4, the absolute value function is continuous, and you can find the limit just by plugging in the number. To the right of -4, the absolute value of x plus 4 is continuous. You can just plug in the number. If I was taking a limit as x approaches -4, then I would be very careful and look at a limit from the right separately from a limit from the left. If I was taking a limit as x goes to -4, because at -4, the absolute value changes its definition. At -1, it doesn't. At -1, you can see it's basically behaving like a continuous function. At -1, I just plug in the number and do whatever the absolute value tells me to do. I just do the definition of the absolute value. Okay, so I hope that's okay as to why I wasn't worried about the absolute value of x plus 4 here. So we can conclude that because the limit exists but the function's not defined at -1, we have a removable discontinuity at -1. I now want to check the other root of the denominator, which is x equal to 3. In this case, I do want to check the one-sided limits. And the reason is x minus 3, if you approach 3 from the left, then x minus 3 will be negative, like if you plug in a 2.9. And x minus 3, if you approach 3 from the right, like plug in a 3.1, it'll be positive. So because x minus 3 is going to change its sign, SIGN, around 3, I really want to be careful here and check the limit from the left and the right, especially because it's making the denominator go to 0. That is also factoring in here. So here, I'm doing the limit as x goes to 3 from the left, because what happens is when you plug in, when you plug in 3, I get 3 plus 4 is 7. I get 7 divided by 0, which is our form number over 0. So now this is the important part. And we know in a one-sided limit, this will be plus infinity or minus infinity. And that's part of the reason I'm taking a one-sided limit. In a two-sided limit, we don't know. You know, I think it's really important to keep in mind the graph of 1 over x as a side comment here, as a comment about these one-sided limits. Think about the graph of 1 over x as x approaches 0. The graph, the limit is undefined, right? Here, limit of 1 over x as x approaches 0, the two-sided limit does not exist, right? It's not infinity or minus infinity. This is a DNE. Because if you look at the two-sided limit right here, approaching 0, from the right, the limit goes to plus infinity. From the left, the limit goes to minus infinity. The two-sided limit does not exist. We have a similar situation here where the denominator is going to 0. And now I want to be careful. I want to check the limit from the right because it might be going to 2 different kinds of infinity. So with this particular problem here, we have number over 0. And now, so I know it's plus or minus infinity. Now I'm checking the SIGN. Here, absolute value of x plus 4 is always positive. X minus 3, if we're approaching 3 from the left, remember what that means. If we're approaching 3 from the left, this means x is less than 3. If x is less than 3, x minus 3 is going to be negative. So here, the answer is negative infinity. And similarly, the limit x going to 3 from the right, again, if you plug it in, you get number over 0 in a one-sided limit that's plus or minus infinity. Here, x is approaching 3 from the right. Numerator is always positive. Denominator is positive if we're approaching 3 from the right, positive over positive. Here we get plus infinity. That's for the one-sided limits. And by the way, you know, the minute we got this limit right here, that this was minus infinity, we already knew that there was a vertical asymptote at 3. Here for completeness, I did the two-sided limit just for completeness. But if they're just asking, does it have a vertical asymptote? Once we get to this, either this or this, you don't need both. Just one of the conditions has to be true for us to have a vertical asymptote.
Wait, I have a question.
Yeah, go ahead.
Okay, so is the reason that you took the one-sided limit of 3 is because when you cancel out the x plus 1 over x plus 1, you still have the x minus 3?
Yeah, and it changes its sign, exactly, yeah.
So, but you don't have to do that for the -1 because they cancel?
Yeah.
Okay.
Yeah, basically, yeah. So here I just did both limits just for completion, just so you'd see what they look like. But if you're asking about vertical asymptotes, if one is infinity, then you can technically stop, you know. And so here we can conclude the two-sided limit, you know, I mean, neither of these limits exist, and certainly also the two-sided limit doesn't exist. We can conclude that because the limit's infinity, we have an infinite discontinuity. So if any one of the limits blows up to infinity, then we have an infinite discontinuity, and it's also a vertical asymptote. So this is just a lot of limits. This whole test is a lot of limits, and I mainly wanted to, you know, show you some limit technique here for vertical asymptotes. For vertical asymptotes, we're looking for numbers that make the denominator 0, and then we're checking the limit. If, you know, the limit from the left or the right blows up to infinity or minus infinity, it's a vertical asymptote, and also an infinite discontinuity. So in the previous problem, I asked about vertical asymptotes, so it seems only fair now to ask about horizontal asymptotes for the same function. So horizontal asymptotes is different from vertical asymptotes. For horizontal asymptotes, we want to take the limit of x as x goes to infinity or minus infinity. When you're making x very large, or going to negative infinity, and you're dealing with a rational function, using dominance of powers is pretty much the way to go. So here, when I look at this function, the thing I want you to be careful of is if I'm doing a limit as x goes to infinity, I want to do dominance of powers. I'm not looking at these terms because x is not the highest order term in the numerator. What we should notice before doing dominance of powers is that in the numerator, there's algebra that needs to be done. So in the numerator, they've given us the polynomial, which should be quadratic. This should be x times x. We should get some quadratic in the numerator. It's been given to us in factored form. So before we do anything, if we need to do some math before we do anything, either multiply this out or see if we can factor and cancel. Okay, so I'll do an example of each technique. So I'm sending x to infinity. I want to use dominance of powers. I need to multiply out the numerator. So let me first figure out what the numerator looks like. Specifically, the absolute value of x plus 4 part. We never got a FOIL rule for how do you multiply parentheses x plus 1 to absolute value x plus 4. We know how to multiply parentheses x plus 1 to parentheses x plus 4, but not parentheses x plus 1 times absolute value x plus 4, right? So here, I need to decode the absolute value first. I need to rewrite the absolute value as a piecewise defined function, and then use the appropriate definition, either x plus 4 when x is bigger than negative 4, or negative quantity x plus 4 if x is less than negative 4. Okay, so here, if we send x to infinity, we can assume, since x is going to infinity, that x is greater than negative 4. And if x is greater than negative 4, then according to this absolute value function definition, I can replace the absolute value with x plus 4. So here, for this first limit, x going to infinity, I do the first technique that I mentioned. So here you have two options. We can either multiply these two out once we figure out this absolute value situation, and then do dominance of powers, or I can try and factor the denominator, cancel anything, and then do dominance of powers, okay? Both should give us the same answer. So here, I replace the absolute value with its definition. So you should notice here, absolute value of x plus 4 gets replaced with just x plus 4, because x going to infinity implies x is greater than negative 4. And then, just for fun, because I felt like it, I FOILed out the numerator. I made sure the highest degree term was in the front. And now for dominance of powers, the only terms I care about are the highest degree terms. The other terms, I'm basically ignoring. And here, x squared over x squared, cancel, cancel. My final answer here, I say, is 1 for the limit. And notice here, you can use dominance of powers on the test. Here I shouted dominance of powers out, right? I say DOP to indicate I calculated this limit using dominance of powers. So here, the limit is 1, but as far as the horizontal asymptote goes, we would say y equals 1 is a horizontal asymptote. We don't want to say the number 1 is a horizontal asymptote. We want to say y equals 1 now is a horizontal asymptote. So, and I'll show you that in a second. I've written it on the last line. Let's do the other limit as x goes to negative infinity. Again, the logic is x is going to negative infinity. So x at some point will be less than negative 4. And by definition, I can replace the absolute value of x plus 4 with negative quantity x plus 4. So here in this limit, I'm going to, in this part, I'm going to do the other technique. I'm going to replace the absolute value. And then instead of FOILing it out, which I could have done, instead of FOILing out, I'm going to factor the denominator and cancel and then do dominance of powers. Just to do it another technique, just to show you a different technique. So here, I factor and cancel, and then now I'm going to replace the absolute value. And then I replace the absolute value with its definition because x is going to negative infinity. So x is less than -4. So absolute value of x plus 4 equals negative quantity x plus 4. And now if you try to apply the limit, you get basically minus infinity over infinity. So now I do dominance of powers, make sure the highest order terms are in the front. Here in the numerator, negative x is the highest order term. In the denominator, x is the highest order term. So cancel, cancel. Negative x over x. By dominance of powers, the limit is -1. And here I mentioned that I use dominance of powers. So the limit is -1. The conclusion about the horizontal asymptotes is that the horizontal line y equal to 1 is a horizontal asymptote, and the horizontal line y equal to -1 is a horizontal asymptote of the function. So certainly, you know, finding vertical asymptotes and horizontal asymptotes are fundamental skills that you should have. So for vertical asymptotes, we're looking for where the denominator is 0 and then checking the limit to see if the limit blows up to plus or minus infinity from either direction. For horizontal asymptotes, we're sending the input to infinity and looking to see if the limit exists. And we're sending the input, the x variable, to plus and minus infinity and seeing if the limit exists. If the limit does not exist, if the limit is plus infinity, minus infinity, or DNE, then there's no horizontal asymptote. In this case, we have, you know, a horizontal asymptote in each direction.
I have a question.
Yes, please.
On the exam, do we have to specify what technique we used?
What do you mean? If you use dominance of powers, you should mention DOP.
Okay.
Just write that, and you're good to go.
I also have a question.
Please go ahead, Brooklyn.
So you FOILed it out for x goes to infinity for that limit, but then you just kept it like FOILed out.
Both work for either. So I can switch these techniques and you get the same answer. You can switch these techniques, you get the same answer.
Yeah, I just wanted to make sure, like, I don't know if there's like a preferred method or something.
No, so you know, I did this way because I felt like it, and then I did this way because I felt like it, and then I thought, well, my feelings are valid, so I just left them, you know. So at the end of the day, you know, at the end of the day, I think the way a human does math is very unique to that person. It's like a thumbprint, and so there's more than one way to do things. As long as we follow the math rules, that's the most important thing, you know. So in both cases, everything I did was mathematically valid, and so at the end of the day, it's okay. And you can use either technique, you know. So good question. Yeah. So you can use either technique. I just wanted to show you the two different techniques, two different approaches. I like to be able to solve a problem in more than one way. At the end of the day, that's kind of what I'm always going for. I like to be able to solve it this way, then I also like to be able to solve it another way. So yeah.
If we're using dominance of powers, do we need to set it up as a limit or?
Well, so dominance of powers typically is only used when we have a limit that's going to plus or minus infinity. So it's a technique that only comes up for limits going to plus or minus infinity.
Gotcha.
Yeah. So here's another limit problem. Remember, this test is primarily limits. And then maybe a squeeze theorem problem or intermediate value theorem problem, you know, and of course, continuity is a very important concept. So here's another limit problem. Remember your procedure. You know, when we get to a problem, we're thinking about it. Maybe we're panicking for like 2 seconds, but then we're saying, all right, I'm done panicking because I don't have time for that nonsense. So then we're going, okay, it's a limit problem. It's not a derivative problem. It's not an integral problem. Right now, that's not an issue, but later. It's limit problems. First thing, let me just try and plug in. When we plug in, we get 0 over 0. So 0 over 0 says we have to try something. So it's very important that I hope you notice, hey, in the numerator, number one, there's fractions. We never want a fraction in the numerator of our fraction. And number two, there are fractions that can actually be added together. So I can combine these fractions. What I'm going to do, you can multiply the first fraction by x over x. And you can multiply the second fraction by 6 over 6. Then you get x over 6x plus 6 over 6x. So that becomes x plus 6 over 6x. So here's my limit. I added the two terms in the numerator, and then I factored out the x plus 6. So here's the x plus 6, and I just pulled the x plus 6 out in front. So the x plus 6 was up here, and then I just factored it out and pulled it out in front. Remember that a over b is the same as a times 1 over b. This whole thing is the 1 over b, and this part is the a. So once I factor out the numerator from the numerator, I can cancel this x plus 6. And now we're back to a limit problem. I mean, even here, before I canceled, if you try to apply the limit, you get 0 over 0. Once you cancel, we're back to this limit, to a limit. Just try the limit again. Just try and plug it in. If it works, great. If it doesn't, we try other techniques. Here, plugging in minus 6, it works out. We get negative 1 over 36. That's the limit. So as I said, we have two named theorems in this class: squeeze theorem and intermediate value theorem. So typically when you have a named theorem, those are the ones we're typically tend to focus on if we have to ask you like a theorem question. So here it says, prove that the function f of x equal to x cubed plus x plus 1 has an x-intercept. I'm coming into this test knowing that this is a Calc 1 test, knowing that the material we're covering are limits, the material we're covering a squeeze theorem and intermediate value theorem. So when I see this problem, it's not like the first time I've ever seen this problem. I've been in the class, I know we've done problems like this. So here I really have to notice that we have a polynomial. It says prove that it has an x-intercept. Doesn't say to find the x-intercept. So I know these are kind of telltale signs for using intermediate value theorem. Here, if I can show that the function f of x, which is a polynomial, which is continuous, if I can show that at some x value, it's below the x-axis, and another x value, it's above the x-axis, then at some point in between those values, it must have crossed the x-axis because of continuity. It can't jump over. There can't be any breaks or holes in the graph. So here, I want to show this equation has a solution that's the same as finding an x-intercept or finding a root. And if you try to solve this algebraically, you cannot. If you try and set that equal to 0 and solve for x, don't even bother. That's the complete, wrong turn to make that'll be disastrous because it'll just waste a ton of your time. So here it's really important to understand it's not asking for a solution, and we couldn't even find one if we tried. So here I first say, look, the polynomial, the f of x is a polynomial, so it's continuous for all real numbers. And now I just want to find x values that are positive and negative. I picked 0 randomly. 0 is my favorite number because it's the easiest one to plug in. I plug in 0 to the function, you get f of 0 is 1. So this is progress. I found an x value where the output is positive, where the y value is above the x-axis. Now I have to find an x value where the y value is below the x-axis. I just tried -1. Again, there's nothing magical about 0 and -1 other than that they're easy numbers to plug in. Will other numbers work? Of course. Plug in -1, I get -1 cubed, which is -1, -1, which is -2, plus 1, I get -1. So what's important here is I found an x value where the output is positive, and I found another x value where the output is negative. And because the function is continuous, it's going to have to cross the x-axis at some point. So here, basically, we've found x values for which the output is less than 0 and the output is greater than 0. And so we've basically shown that 0 is in the range of this continuous function, and it's going to have every number in between is going to be attained by the function because of continuity. I can't go from below the x-axis to above the x-axis without crossing the x-axis if you're a continuous function. So that's exactly what happened here. So the theorem that I'm describing is called the intermediate value theorem, and so I want to shout it out. So because of the continuity, because of the fact that 0 is a number in between f of a and f of b, f of -1 and f of 0. There exists a number c in the interval -1, 0, such that f of c equals 0. And this is exactly the equation we're trying to show has a solution. So here we haven't found the solution, but we've shown that this equation has indeed such a number does exist. And so, we can conclude the polynomial has an x-intercept. As I said, in this case, trying to solve this algebraically is a huge mistake. We cannot solve this problem by hand. At the end of the day, using the intermediate value theorem and using a computer is really one of the best ways we have to answer, but here, of course, this was just the intermediate value theorem. I just want to show the existence. So yeah, so you can expect, intermediate value theorem is fair game. Squeeze theorem is also fair game. So here I'm going to do a squeeze theorem problem. So on this slide, there's two questions. The first question asks, is the function, the given function here, x times sine of 1 over x, even, odd, or neither? And then the second question says, find the limit as x approaches 0 of x times sine of 1 over x. And then they say, what's the value of f of 0? So for the first part, we want to use the definition. I want to plug in negative x into the function. And if f of negative x equals f of x, then it's an even function. If f of negative x equals negative f of x, it's an odd function. If f of negative x equals neither, then we have a function that's not even or odd, okay? A function doesn't have to be even or odd, it can be neither. So here I plug in a negative x everywhere an x is occurring in the function. And we know, it's a known fact that sine is an odd function. So this minus sign here, I pull it out because the trigonometric function sine is an odd function. You can show that with the graph or using trig identities. And it's just a known fact in this class. So now the minus, and there's a minus here also, the two minuses cancel, we get back the original function. So here we can conclude the function is even. And if you didn't get a chance to check your email, in the slides I sent you, there was a typo here. In the slides I sent out yesterday, I had a mistake and it's had odd written here, which is odd, which is wrong. And I corrected that and I emailed out a new set of slides, but if you I emailed them out at after my morning class or my other class around 2 o'clock. So if you haven't checked your email since around 2:30 or before this class, your slide will have a typo on it. It should not say odd, it should say even. Okay, I'm sorry, my bad. I may not pass calculus this time, we'll see. So here the function is even, and that's great. For the limit, actually, for the limit, we could use the even property, but for the limit, I want to make one main comment is first, I want you to notice this is different. This is not our special limit. It's not the limit of sine of x over x as x goes to 0. First of all, the reciprocal, the 1 over x is happening inside the sign. Right here, the 1 over x here is happening inside. And so one comment to make is, hey, Suji, why don't we write the x in front as a reciprocal? So here, instead of multiplying by x, so let me get rid of this x here. Instead of multiplying by this x, let's write this as sine of 1 over x divided by 1 over x. Then it starts to look like our special limit. But no, it isn't our special limit, because our special limit, if you look here, yeah, this is the same as sine of blah over blah. We got that part. Sine of here, blah over blah. Okay, we got that part. But the blah is going to 0. That's what's different. Here, when x goes to 0, 1 over x is undefined. You remember the limit for 1 over x as x goes to 0 from the right goes to plus infinity. As x goes to 0 from the left goes to negative infinity. The two-sided limit as x goes to 0 is a D and E. So this is not the special limit. this limit and this limit, even though it sort of looks the same, are not the same at all. And so here, because this limit doesn't exist, when you do sine of 1 over x as x goes to 0, that just doesn't make any sense because 1 over x doesn't make any sense. This is considered an indeterminate form. And here we have to try something. And here, because I know the sine function can be bounded with an inequality, I'm going to try and do a squeeze theorem. Here, I'm going to look at this two-sided limit. I'm going to break it down into a one-sided limit. I'm going to check the limit as x approaches 0 from the right. And then I'm going to check the limit as x approaches 0 from the left, okay? Because 1 over x, I understand a little better the behavior of 1 over x if x is approaching 0 from the right. I know it's blowing up. Or if x is approaching 0, I have a little bit of understanding. And plus, we'll be able to manipulate the inequalities better. So here, if x is greater than 0 for our limit from the right, I can multiply this inequality here through by x without changing the direction of the inequality because x is positive. Now, squeeze theorem says we can just take limits, just slap limits here. The inequalities are still true. So now I can take the limit of the function at the very ends here. The limit of negative x and the limit of x as x approaches 0 from the right is 0. So by the squeeze theorem, the function in the middle here has to also go to 0. It's being squeezed on either side, has to go to 0. And actually now we can use the fact that this is an even function. If you think about the geometry of an even function, the limit from the other side, because it's a mirror image, the limit should be the same. And you can make that argument. I didn't really think about it. I just did the squeeze theorem argument again, but for the limit from the left. So now I'm assuming x is less than 0. So look what happens. Start with the identity, multiply by x, and because x is less than 0, in this case, the inequalities flip around. Remember here, negative x is actually positive. The minus sign doesn't mean anything because x is a variable. And here x is assumed to be less than 0. So here negative x is positive, and here x is negative because x is being assumed to be less than 0 here. The inequality signs turn around. That's fine, no problem. Hit it with a limit. And now calculate the limits of the functions on the very left and right end. So they go to 0, thus the two-sided limit is 0. And here I want to mention here, the actual function is undefined. So again, here we have a removable discontinuity. The limit exists, but f of 0, if we try to plug in 0, this part makes no sense. So the actual function is undefined, but the limit exists. Yeah, so here, this is a removable discontinuity in the graph. The limit from the left and right exists, but there's no actual function at the point. So this was the question that was asked. Unfortunately, it's right at the end, but this is important for continuity. Let me just mention, remember continuity is a limit definition. So here for continuity at x equal to 0, we need this limit to be true. In general, the continuity at some number a would say the limit of f of x as x approaches a has to equal f of a. Here a is 0. So it's really important to check this. But remember, this is saying 3 different things. This is saying number 1, the right-hand side has to exist. This is saying number 2, the left-hand side, which is a two-sided limit, has to exist, which means the one-sided limits have to be a finite number and have to be equal. And finally, the third thing we're saying is that the two-sided limit on the left-hand side equals the function value on the right-hand side. So there's 3 things we're trying to be mindful of. And in this problem now, all I'm doing is calculating each one of these things and setting them equal to each other. So really quickly, the limit from the left, when x is approaching 0 from the left, that means x is less than 0, so I'm using this function. And now we have our special limit. Here's sine of x over x as x is going to 0. So by our special limit or squeeze theorem, this is 1. So that's a known fact in this class. The sine of x over x as x goes to 0 equals 1. So the limit from the left is 2. For the limit from the right, remember, x approaching 0 from the right means x is bigger than 0. So I'm going to use this function in my limit. And it's a limit, just plug in the number. So I take x and plug in here, b times cosine of 0 is just 1. So the limit from the right is b. So now I'm going to set all three of these things equal together. Look, f of 0, when x equals 0, the function output looks like 3a. So I'm going to set the two limits equal to each other and also equal to 3a. So here's our limit from the left. I'm going to set it equal to the limit from the right. I'm going to set it equal to f of 0. So here, our limit from the left, our limit from the right, and the function value. Set them all equal to each other. And now solve for the unknowns. So a equals 3 over 2, and b equals 2. The next two slides are absolute value problem and another limit problem. I'll let you look at those. But the slides we've covered are really good and are really good review. And all of these topics that we've covered are relevant. Okay, so please have a look at these and double check that this looks okay. All right, everybody, I'm going to stop right here.